Today we are going to be talking about optimization. To solve problems involving optimization, draw a picture. These problems really require that you get a good look at what you're trying to find. Label your dimensions in terms of one variable, usually x. Find a function in terms of x to represent what the minimum or maximum value you are trying to find. Be sure to define the domain for x. Take the derivative, set it equal to 0, and find the critical points. Check the critical points and don't forget the endpoints. Here we have a classical problem. You have 40 feet of fence to enclose a rectangular garden. What is the maximum area that you can enclose? A of x is considered to be the area formula as a function of x. The domain is the area between 0 and 20 feet. To find the maximum value of a of x, we take the derivative, set it to 0, and solve for x. After the distribution of x over here, you took the derivative, set it equal to 0, and solve for x. And plugged it back in to find the other part of the equation. Here's another problem. You have 40 feet of fence to enclose a rectangular garden along the side of a barn. What is the maximum area that you can enclose? W equals to x. And this is the equation that we get for the length. So the area is this equation right here. A equals x times 40 minus 2x. To find the maximum area, we distribute the x, find the derivative, set it equal to 0, solve for x. X equals 10. There must be a local maximum here since the endpoints are minimums. So w equals to x and x equals to 10, so w equals to 10 also. So after plugging it back into the L equation, we get that L equals 20 and w equals 10 feet. Now to find the area, we have to plug in these two into our normal equation. No, we plug in the 10 into our normal equation, plug it into x, and we get 200 feet squared. Third example. What dimensions from 1 liter cylindrical can will use the least amount of material? So we can minimize the material by minimizing the surface area. That part is the area of the ends, and that's the lateral area. So we need another equation that relates R and H, which is the volume equation. So 1 liter equals to 1,000 centimeter cubed. So we plug that into the volume equation for V, solve for H, and we plug that in back into the area equation as we plug it in for H over here. So we plugged in the answer we got over here to here. Cross out. Find the derivative after crossing out. After we find the derivative, we set it equal to 0 and just solve for R. R equals cube root of 500 divided by pi, which is approximately 5.42 centimeters. So we plug that back into what we got for H. H equals 1,000 over pi times 5.42 squared, and H is approximately 10.83 centimeters. Some notes and reminders to be kept about optimization. If the function that you want to optimize has more than one variable, use substitution to rewrite the function in terms of just one variable. If you are not sure that the extreme you found is the maximum or minimum, you have to check. If the endpoints could be the maximum or minimum, you have to check also. And that's it for my video.